In the previous session, we saw how we can use the mass of elements in a compound and also percent composition of a compound data to figure out the empirical formula of the compound. There is another set of data that can be used to determine the empirical formula of the compound, and this data comes from combustion analysis. Basically, a compound is burnt in air in presence of oxygen gas, and the results of that are then used to determine the empirical formula of the substance. So, this presentation, this session will focus on that um, data. Now, before we actually look at specific problems that allow us or ask us to solve for the empirical formula using combustion data, just a little bit of background information on for combustion reaction itself. We will not be going into details of combustion reactions or any different kind of reaction for that matter in this class. That is for later on. But as far as combustion reaction is concerned, specifically, and this is something you need to note, specifically for compounds that are made up of carbon, hydrogen, and or oxygen. Only for those, and those are the specific ones we will deal with in this session. Combustion reaction itself means burning in air. And when we say air, we are really saying oxygen. In other words, we are talking about oxygen gas, which is O2, free oxygen, stable oxygen that exists in air. So we are talking about aerobic combustion in this case. So combustion of a compound, please assume that it is burning, but burning in presence of oxygen gas. It's a chemical process where the substance that is being burned reacts with the oxygen gas in the air. It's a chemical process that then creates compound substances that did not exist before. In case of compounds that are made up of carbon, hydrogen, and or oxygen, when reacted with oxygen gas, when burnt in presence of oxygen gas, will produce carbon dioxide and water as the products. This is of course assuming that the combustion is 100% efficient and therefore none of the side products are explored here. So when you are looking at combustion reactions for these kind of compounds, the equation, the reaction equation looks like this. Now we haven't written reaction equations, and we will write many more in the next chapter, but this is just an FYI that what we are saying here, it's actually a statement. It's not a mathematical equation by any means. A reaction equation is a shorthand notation that says that these two substances, in this case two, it can be any, but CXHYOZ and the plus sign here means to say and oxygen gas together combine chemically to produce, and then the arrow shows the direction of the transformation, to produce carbon dioxide and water as the products. These are called products and these are called reactants. So we start out with reactants, we use the reactants to make the products. Okay, so with this background information, let's solve a problem such as the one here to figure out the empirical formula of this compound that is made up of C, H, and O, excuse me, no O, I'm sorry, contains C and H only, such a way that its combustion analysis yields 3.14 grams of CO2 and 1.29 grams of water. So if you remember from the previous slide, if we write an equation, so we do not know the subscript X, we do not know the subscript Y either, but the compound has only carbon and hydrogen. It reacts with oxygen gas in the air when it's burned, when it undergoes combustion, to make carbon dioxide and water. Okay, so the data also says to us that 3.14 grams of CO2 was isolated with 1.29 grams of water. Okay, so now how from this data, how do we go to figure out the empirical formula of this compound? Please once again remember that the empirical formula gives us the lowest whole number ratio of moles of elements in that compound. In other words, we need to figure out the lowest whole number ratio of moles of carbon and hydrogen in this compound to figure out the empirical formula. In order for us to figure out that, we need to first determine the number of moles of carbon and the number of moles of hydrogen. How do we do that? Can we in some way figure out the number of moles of carbon from grams of CO2? The answer is yes, we did that in the previous problems, quite a few of them. Can we figure out the number of moles of hydrogen from grams of H2O? Absolutely, you can. You please remember that grams of CO2 can be converted to moles of CO2 using molar mass of CO2, which can of course be converted to moles of carbon using the subscripts in CO2. Similarly, grams of H2O can be converted into moles of H2O using molar mass of H2O, which can then be converted into moles of H in H2O using the chemical formula. I hope this rings a bell from the previous examples that we've solved or from the homework assignments. Okay, so let's set it up. We need to convert 3.14 grams of CO2. First, grams of CO2 goes to moles of CO2, and then moles of CO2 goes to moles of carbon in CO2. Now if you look at the numbers, the molar mass of CO2, 1 mole, molar mass of CO2 is 44.01 grams. And then from the chemical formula, 1 mole of CO2 has 1 mole of carbon. If you solve this, we get 0.07134742 moles of carbon, which should be rounded to 3 significant figures based on the data given, and that becomes 0.713 moles of carbon. Similarly, if you set up for water, 1.29 grams of H2O first goes to grams of H2O to moles of H2O. Moles of H2O converts to moles of hydrogen in H2O. Once again, using molar mass, 1 mole H2O has a mass of 18.02 grams, and 1 mole of water has 2 moles of H from the chemical formula. If you solve this, we get 0.1433748 moles of H, rounded to 3 significant figures, gives us 0.143 moles of H. So now let's take stock of what we know. We know our compound is made up of C and H. We know from our calculation that it has 0.713 moles of carbon and 0.143 moles of hydrogen. What's the next step? Absolutely. The ratio of moles of these elements calculated by dividing each of them. I'm sorry, I made a mistake. I forgot this 0 right there. Yes, there is a 0 there. So this is 0.0713. My mistake. Okay, so we figure out the ratio by dividing each of the moles by the smaller one. The smallest, of course, is moles of carbon, so we get the ratio rounded to a whole number, 1:2. If that is the case, the empirical formula for this compound equals CH2. Okay, let's look at the next problem. It's a similar problem in the sense that it also deals with combustion analysis data of a compound, in this case that is not just made of carbon and hydrogen but has carbon, hydrogen and oxygen. In other words, CxHyOZ reacts with oxygen gas in air when burned to make carbon dioxide and water. The data given tells us that when 3.750 grams of the compound was burned, it led to the formation of 10.05 grams of CO2 and 2.47 grams of H2O. And we need to determine the empirical formula of this compound. So once again, please remember that empirical formula gives the subscripts give us the lowest whole number ratio of moles of all the elements. In other words, in this case, we need to figure out moles of carbon, moles of hydrogen, and moles of oxygen. And that's the tricky part. Moles of oxygen have to be only the moles of oxygen that are present in this compound. In other words, only the OZ, should not include the oxygen gas, not include O2 at all. So that is the trickiest part. But as before, as in the previous problem, we can convert grams of carbon dioxide to moles of carbon dioxide. Moles of carbon dioxide can be converted, of course, to moles of carbon. Similarly, grams of H2O can be used to figure out moles of hydrogen through moles of water. Now we already set up this problem, these calculations in the previous problem, so please pause the recording at this time and go ahead and calculate the number of moles of carbon and the number of moles of hydrogen using this data. So when you do that, the number of moles of carbon comes out to be, without rounding, I'm not rounding just yet, 0.228357192 moles of carbon. And moles of hydrogen comes out to be, that's carbon, 0.27413,985 moles of hydrogen. Okay, so I haven't rounded yet. These are the number of moles of carbon and hydrogen we calculated. Now from here we have to figure out, how do we figure out the number of moles of oxygen, only the part that comes from the compound? Exactly. So first you have to figure out the mass of oxygen from this compound only. How do we figure that out? Mass of oxygen can be figured out. Mass of oxygen can be figured out by subtracting from the total mass of the compound. If you subtract the mass of carbon and the mass of hydrogen, the difference will lead you to the mass of oxygen only. So do we know the mass of carbon? Well, we don't, but we do know moles of carbon, so we can figure out the mass of carbon. Similarly, we can figure out the mass of hydrogen as well by using the molar mass of carbon and molar mass of hydrogen. So if you convert, and let me just separate it here, you can multiply this by the conversion factor. 12.01 grams of carbon is 1 mole of carbon, so that you can then convert this into grams of carbon. Rounded to 4 significant figures gives us 2.743 grams of carbon. Similarly, if you multiply the moles of hydrogen by the molar mass of hydrogen, 1.01 grams of H for every 1 mole of H, crosses out, and that gives us, rounded to 3 significant figures, 0.277 grams of hydrogen. So if you substitute those numbers, 3.750 minus 2.743 plus 0.277 gives us the mass of oxygen as a certain value. Okay, you can calculate it, of course. I will just move on to the next step. Okay. How do we calculate the moles of oxygen? The moles of oxygen come from the mass of oxygen by moles of oxygen will be Therefore, 3.750 minus the sum of mass of carbon and mass of hydrogen. This is all in grams of oxygen. Of course, that can be converted to moles of oxygen using molar mass of oxygen. And when you calculate this, we get a calculator answer equal to 0.045625 moles of oxygen. So now let's take stock of what we know, and this time we will go ahead and round to the correct number of significant figures. We know the compound has C, H, and O. We know that the number of moles of each of those for carbon in 4 significant figures will be 0.2284 moles. For hydrogen, to 3 significant figures will be 0.274 moles, and for oxygen in 3 significant figures will be, so we're going to round it off right there, will be 0.0456 moles of oxygen. Once you know the moles of all the elements, the next step is the whole number ratio by dividing each of the moles by the smallest. When you do that, the whole number ratios come out to be as such, which means that the empirical formula for this compound equals C5H6O